Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. The topic for today's lecture is Material Property Chart, Indices and Concept of Hybridization. In the last lecture, we discussed about some material property charts, specifically modulus versus density plot, strength versus density plot, and then these two plots were combined together to show specific modulus versus specific strength plot. And then we briefly introduced the concept of material indices through one case study. In this lecture, we will show the combined use of material property charts and material indices after a brief after the remaining discussion on the material index introduced in the last lecture. It will be followed by the introduction of the concept of hybrid materials and the possibility and idea of hybridization, and finally, the lecture will be concluded with the concept of FGM or functionally graded composite materials. The keywords for this lecture are property charts and material indices, materials selection for a light stiff beam, hybridization, best of two scenario, rule of mixtures, harmonic mean, list of two scenario, and FGM. So, this is the follow up from the last lecture, where we saw that to minimize the mass of the light stiff beam, we obtained this expression for the mass of the beam, that is in small m, where the parentheses shown in green color are the terms already defined by the constraints of the design. That means, S was the stiffness, L is the length of the beam, and C1 is a constant. So, that actually leaves us with this purple marked portion, this rho over e to the power half, and this is actually the so called material index, because both rho and E are material parameters or material properties, and these can actually be optimized to actually minimize the mass of the beam. That means, the proper material selection will actually give us the lowest value of the m. Now, this material index, which is also kind of given as capital M, is actually given to maximize something. So, although in this expression it is given to minimize the mass, and this is by kind of minimizing rho over e to the power half, when it is expressed for material design purposes, it is written that the other way around. That means, you have to maximize the parameter e to the power half over rho. And how this can be obtained? This is simply obtained by plotting, again making a plot of Young's modulus over density, again double log plot, and now because the parameter is now e to the power half over rho. So, one has to now draw a line of slope 2 in this particular curve. So, there are several lines of slope 2 drawn in this plot, and I have actually marked one line with the red dashed line, and that is also a slope of line 2 in this particular plot. And what do you see from here? This actually shows us a very interesting conclusion. We can see that the line actually passes through almost the middle of the foams, also through natural materials, composite materials, and ceramics, and almost all the metals are actually performing poorer, because the concept is that, as I discussed in the last lecture, all materials lying on the same line are equally good for any particular application. Materials lying above are better, materials lying below are actually inferior. And because almost all the metals are lying below the red dashed line, so when it is coming to a light stiff beam, metals actually perform inferior to almost all the cellular solids. Another important conclusion is that the wood, which is a natural cellular solid, is a very good material for this kind of applications. And this is a reason that if you see in many countries, wood is actually used for building applications, and this is because wood is a very good material for light stiff material for bending applications. Metals are very much inferior to wood in this particular aspect. So, what we learn from this particular diagram is that again the proper material selection is very important, and again natural materials or cellular materials or composite materials can actually give you a very nice opportunity to actually design your material with new novel concepts, which can actually exclude more conventional materials because they might be more dense, they might be less stiff and so on. So, with this thing now we can see that we just introduced one such material index like e to the power 1 by 2 over rho, but there can be many such material indices, because a material index is nothing but a combination of different material properties. That means, to devise or to design a material index, one simply needs to understand which performance or which function a particular material needs to perform, and then which parameters actually control the performance of those components, and then actually make or create a relation between those individual properties of the materials and tie them together in such simple forms which are known as the material index. And then if the material index is either maximized or minimized, the intended function of the component will be also maximized or minimized as intended. So, in this class already we have seen two such material indices. Today we have discussed about the e to the power 1 by 2 over rho, and in one of the previous lectures we discussed about the spring with minimum weight for given energy storage, and that was sigma y square, that is the yield strength over E multiplied by rho, and we also discussed about the minimizing the cost of the material. So, we can also bring cost as a parameter and in denominator, and that will again give a new material index sigma y square divided by E multiplied by rho multiplied by C, and this way as a materials engineer for a material selection purpose one can actually design or create several new material indices. Many such material indices for some standard applications have been shown in the book of Mike Ashby on material selection for mechanical design. So, next we go a bit deeper and more towards the hybrid materials development. So, in this section I will show you the combined use of property charts and indices. That means, until now we have treated the material property charts and the material indices as separate entities. So, now the idea is that how we can combine the idea of the material indices and the material property charts in one entity to actually help us identify the best material for any application. So, again we start with the Young's modulus over density plot, and the aim is to select a material with a low density, sufficiently high Young's modulus and a function which will maximize e to the power 1 by 3 over rho. So, in terms of to reduce the density and sufficiently high Young's modulus, we actually kind of select a region which actually gives us a density less than 3 kilogram per meter cube and Young's modulus more than 10 gigapascal. That means, the pink colored box or pink rectangle which you see on the top left portion, that is the area of interest. That means, you can already see that already our selection of the region, that means this less than 3 kilogram per meter cube density and more than 10 gigapascal Young's modulus has already rejected or kind of omitted bulk of the materials. That means, all the foams are out, almost all the metals are out, many of the ceramics are out, and also many of the polymers are also out of our initial selection criteria. So, next we move on to our next condition, that is we have to maximize the material index e to the power 1 by 3 over rho. Again, as we saw in the last lecture, if we have to find out the line for this index, because e to the power 1 by 3 over rho and it is a double log plot, it is simply the contours of lines having slope of 3. So, these slopes are being shown over here, and you can see, I mean, in this particular curve or in this particular plot, 3 slopes are being shown. The line for the slope of 1, which is e over rho, the lines for the slope of 2, that is e to the power 1 by 2 over rho, and the lines for the slope of 3, that is e to the power 1 by 3 over rho. And for our interest, we now concentrate on the e to the power 1 by 3 over rho, that means the lines with the slope of 3. So, here only the lines with the slope of 3 are shown, and you can see all those 4 or 5 dotted straight lines, they actually belong to different values of e to the power 1 by 3 over rho. So, as we have already discussed that the concept of these material indices and these contour lines actually tell us that all the materials lying on the same line are equally good for any particular applications. Materials lying above are better, materials lying below are inferior. That means, all the lines or all the materials which fall on the line showing a value of 0.5, that means that if you calculate the value of e to the power 1 by 3 over rho for all those materials, you will obtain a value of 0.5. So, this way, that means as we move from 0.2 to 5, we are actually improving, although the material parameter or the material index is remaining the same, the actually the overall value of the material parameter e to the power 1 by 3 over rho is actually increasing as we move from the line for 0.2 to 5. So, in this slide what we have done, in this slide now we have actually combined the two different concepts together. We have taken as our standard e to the power 1 by 3 over rho equal to 2. This is the material we have selected, or this is the value we have selected for the particular application. We could also select any other value like e to the power 1 by 3 over rho for equal to 0.5 or 0.2, whatever we intend. That will actually be controlled by the final materials performance intended. But in any case, we have now selected e to the power 1 by 3 over rho equal to 2, and then we again actually combine with that we have previous condition that the density should be less than 3, and we now have added one more additional criteria that the Young's modulus should be more than 50 gigapascal. And then you can see, if we have such stringent criteria, that we have such stringent things, we actually end up with very few materials that actually fulfill our conditions, like only some composite materials, very few ceramics, and some metals like some lightweight metals can actually fulfill this design criteria. Now, this is one way of actually selecting the material starting from a very vast range of materials and also kind of zeroing down your choice to only a few materials. But nevertheless, one should never forget that this is not the end of the story. We have now selected only a few materials based upon whatever stringent criteria we decided, but then the final material selection will again be decided by several other factors, like as I mentioned previously, cost of the material is one very important factor. Like there might be applications where, for example, the cost of the component will be so high, like if you want to fabricate a component of carbon fiber reinforced composite, which is a very nice material for many applications, but the cost is really prohibitive. Like if you see those bikes, the carbon bikes which the professional bikers use, they can easily cost you more than 1000 to 2000 euros or something like that, whereas the normal aluminum bikes which common people we use, they may be something like 100 euros or something like that. That means again cost is a very important factor. The application of ceramics, whenever ceramics are put into application, they might be having excellent properties like specific stiffness, but before applying any ceramics into application, the first and foremost thing that needs to be considered is the high brittleness and the low fracture toughness of the ceramics, and then again the fabricability. If whatever material is being selected, whether the material is fabricable at the given conditions. So, many a times, although the manufacturers or the engineers, they know that an alternate material might give actually better properties, they have to actually compromise for a lesser material, because the prevailing conditions will actually provide a better kind of fabricability, better marketability of the material, which is actually providing a lesser properties. This is a real engineering problem which needs to be understood from all the aspects. So, next, after we discussed all these concepts about material selection process and a combination of different ideas, next we move on to the basic or the main theme of this course, that is the hybrid materials. And before we move to more deeper concepts, first I will show you what are the possibilities of hybridization. That means, what do I mean by that? The diagram in this particular slide actually shows you this question, that possibility of hybridization. That means, we have here two materials. That means, as you know, a hybrid material is generally a combination of two or more materials. So, here we take the simplest condition or simplest case, where two materials are combined in one material to give one hybrid material, material 1 and material 2. And generally, as we have seen in the material property charts, typically we try to combine in a material property chart, we combine two different properties, property P1 and property P2. Very often, as we have seen already, property P1 along the x axis is very often density, and property P2 can be other properties like strength, stiffness, fracture toughness, thermal properties, many other properties. Now, for any material, be it a metal, be it a ceramic, be it a polymer and so on, whenever you take two properties like P1 and P2, they will actually give you one point in the material space, as is being shown by the circle M2 and M1. So, now the question is that how should we hybridize to get different properties, and that actually gives us 4 different conditions or 4 different options of hybridization. One is the best of both scenario. That means, in this best of both scenario, as you will be seeing afterward, the aim is to obtain the best properties of both the materials. The second and third are actually more commonly observed for composites material design. The second one is called the rule of mixtures, and the third one is called the harmonic mean, and then the last one is called the least of both options. So, we start with the first option, which is the greatest of both option. That means, we want to design a hybrid material which will have the best properties of both the conditions, and believe me, this is not trivial. So, that means, what we are trying to obtain is that we will design a material which will actually provide you the best properties of both the situations, and for this particular situation a special type of composite materials are required or generally required, which are known as functionally graded materials. So, typically you assume that you obtain or you try to obtain a material, for example, which will give you both a combination of very high hardness or very high wear resistance combined with a very good toughness. And as a materials scientist or materials engineer, we know that it is not easy, because normally toughness and strength, they do not go hand in hand. For materials like metals, for any strengthening mechanism which will increase the strength or hardness will typically reduce the toughness of the material. So, to solve this kind of a problem, scientists actually came up with this kind of a material, which is called a functionally graded material. So, you can see this is one composite or one sample where the top layer is actually made up of metal, like it is a pure aluminum material, and the bottommost layer, as you can see, there is a distinct texture difference from metallic luster to dark luster. This complete dark phase at the bottom is actually a very high amount of silicon carbide, which is a ceramic, and as you go from top to bottom, your SiC or silicon carbide content in the whole material actually continuously increases. So, this is a material where the composition is actually changing from one surface to another surface. That surface with the high silicon carbide content will give you a very high hardness and wear resistance, whereas the surface with the very high metal content will give you a very high toughness or a soft material, and that will actually give you a combination of good toughness and hardness where you require. And this is one concept of hybridization, which is called the best of both scenario. And many such designs of FGMs or functionally graded materials can be actually created, and some examples are shown over here. And actually, for your information, many of the natural elements like the bone of our body or our teeth or the wood, for example, many of these components are actually naturally graded components. The second option after this greatest of both option, the second option is called the arithmetic the rule of mixture. The rule of mixtures concept is actually very common for composites material development, and again I discussed at the beginning the concept of your fiber reinforced composites, where the fibers, if we again assume a fiber reinforced composite, like fibers are all along one direction, and if we assume that the material, there are two materials, material 1 and material 2, and the volume fraction of the two materials are like V1 and V2, then the simple expression which you will see afterward also, for the composite Young's modulus along the one direction, that means EC1 is nothing but your E1, that means the Young's modulus of the phase 1 multiplied by the volume 1 plus E2 over V2. That means you have the volume fractions of the individual components and the Young's modulus of the individual components, and the simple rule of mixture, the arithmetic mean, will actually give you the modulus of the fiber reinforced composite along the fiber direction. And this is very often, this is a very important equation. This is also called the Voigt bound or the upper bound, and this is a very important relation which actually controls or decides the Young's modulus of continuous fiber reinforced composites. However, as I told you earlier also, that the fiber reinforced composites are very much non-isotropic materials, and the material properties differ a lot along both one direction and two direction. That means, in this particular design, along one direction the equation is being shown over here. However, if one needs to find out the same modulus along two direction, that means the expression for EC along two direction, then one needs to use this equation. So, 1 over EC2 equal to V1 over E1 plus V2 over E2. So, this then becomes the harmonic mean. That means, and this is also called the lower bound or the Royce bound. And actually, you will see afterward in the part on the composite materials that the modulus of composite material, if you have two materials and if you just simply plot like here the E and here your one material and here the other material, then this is the initial Voigt bound and this is the Royce bound, and the modulus of the composites will always lie within this bound. So, this way we again see that the two bounds have been introduced. One is the rule of mixtures giving the upper bound, which is the arithmetic mean or the Voigt bound, and the harmonic mean or the inverse rule of mixture, which actually gives you the lower bound or the Royce bound. And the final part of selection or the final option of selection is the least of both. This least of both is also sometimes appropriate for designing purpose. For example, if a design is planned where it is a fail safe design, that means the weakest component should fail first. so that the whole component will remain intact without failing. And this is the least of both. That means the aim of the component of the hybrid design is to obtain the least property which will fail first, giving the best combination of properties to survive the test. So, overall we have seen that this is the overall concept of materials design. That means, if we only, that means just imagine very primitive applications where one material might solve all the problems. For example, simple utensils, for example, there you do not really think of hybridization because the price will be too expensive for that. So, for such applications where the price and the requirement are not critical at all, in those applications only one material will solve all the problems and only one material is sufficient. It is a simple solution as shown by the arrow on the top portion. But suppose we have more complicated applications, for example, aerospace components, for example, for thermal applications, for example, for many automotive applications. In those applications, only one particular application or one particular material is almost never sufficient, because no material, no single material meets all separate functions. That means, we have in those materials what we require is so called multifunctionality. That means, we need one function, like for example, increase the specific stiffness, increase the specific strength, at the same time the thermal properties should be good. That means, no one material will give you a combination of all the properties. So, what we do? We then have to combine the solutions, we have to assess their performance, and there actually the choice of configuration plays a very important role, and this is actually the point where hybrid materials comes into picture. We need to consider the composite materials, sandwich materials, lattice materials, and also how to create those materials. What about the interface? What about the fabrication, like your how to actually combine the metal and the ceramic together? It is not a trivial job. And then after all these things, you actually end up with one hybrid solution. But again there can be many cases where these monolithic hybrid materials are again not sufficient, like as we discussed in the previous cases, we saw there are 4 concepts of hybridization. And if you want the best of all the situations, then these monolithic hybrid materials are often not sufficient, and you may have to go for the advanced composite materials like FGM materials. So, overall in this lecture we have learned quite a few things. I showed you the trend lines in the material property charts with a particular value of the material indices, and we also discussed that all the materials lying on a constant value of the material index contour are equally good. Materials lying above are better, materials lying lower are inferior. We typically showed that wood, for example, could be a very nice material for light stiff beam applications, whereas many metals like steels, because of their high density, are inferior to woods. Then we learned about the different concepts of hybrid material development. There are 4 different concepts we learned, that is the best of both scenario, rule of mixtures, harmonic mean, and the least of both scenario. And we also discussed briefly about the basics of FGM or the functionally graded composite materials. As for references, I refer to the book of Mike Ashby and some research articles by Oja et al. And Zhang et al. In the next lecture, we will discuss about the composite design for stiffness at minimum mass, also design to minimize thermal distortion. So, how composite materials are designed to minimize both thermal distortion and also increase the specific stiffness, and also we will discuss about the advantages, disadvantages and applications of composite materials. Thank you very much.